In this work, we describe the very first selenolate protected silver cluster which has a similar optical absorption spectrum as the thylated Ag44 cluster. Motivated by the recent studies on silver clusters, which are mostly thylated protected, we tried to synthesize a selenolate analog through a solid-state route. In this synthetic protocol, silver nitrate has been taken in a mortar and pestle and ground well. To the mixture, benzene selenol was added. After a few minutes of grinding, solid NaBH4 was added. Upon continued grinding, the color changes to greenish brown. Extraction by ethanol followed by centrifugation and subsequent dissolution of the centrifugate in acetonitrile or acetone, we get the purified Ag44 cluster, which is dark pink in color. This is the UV visible spectrum of asynthesized Ag44 SeR30 cluster. The red trace shows a comparison with the thylated Ag44 data. Most interesting part is the exact match of the spectrum with the calculated spectrum of the selenolate protected cluster, which is shown as the dashed line. The structure of the thylated analog has been used as a starting point in this calculation. Mass spectrometry is an ideal tool to identify the system precisely. This is the high-resolution ESI mass spectrum of Ag44 SeR30 cluster, which shows the presence of 2 negative, 3 negative, and 4 negative charged ions of the cluster. Absence of any other peak suggests the high purity of the cluster. Below is the extended mass spectrum of the 2 negative ion, which shows an almost exact match with the corresponding calculated spectrum. Several other characterization studies were done to understand the system in more detail. Thermogravimetry is an agreement with the composition and mass loss started at 200 degrees centigrade, which suggests a reasonable stability for the cluster. Average core size of 1.1 nanometer was confirmed from TEM analysis. XPS shows zero oxidation state for silver. Selenium 3D binding energy corresponds to the selenolate species. Calculations of Ag44 SeR34 negative confirms a similar structure as of Ag44 SR34 negative. It has an icosahedral core surrounded with another hollow cage of 20 silver atoms, which is further connected with a cell consisting 6 Ag2 SeR5 staples in an octahedral fashion. In summary, we report the synthesis of a highly stable selenolate analog of the Ag44 cluster. The optical properties of the cluster are supported by TDFT computations.